Hello everyone. So we're going to be going through actually the last section of your notes, so we're skipping one. And it's talking about binomial expansion. So what this actually is, it has to deal with multiplying out a binomial to an exponent. So for example, this x plus y to the 10th power here. So to do this algebraically, it would get really long and obnoxious. So we're going to see if we can find some patterns to make it a little easier. So when binomials are expanded, is there any type of pattern developing which might help us expand more quickly? So I'm going to do some expansions here. You're going to have to take my word for it that that's what they work out to be. If you want to do it on your own, you're welcome to. But I'm going to give you the first couple terms here. So as we know, anything to the 0 power is just going to be 1. X plus y to the first power is just going to be x plus y. Now, we're going to use x plus y, that one before, and we're going to multiply it by x plus y again. Write a little smaller here. X plus y times x plus y. And that actually ends up to be x squared plus 2xy plus y squared. If we go on to the next one, to the third power, that's going to be x plus y times x squared plus 2xy plus y squared. And as you know, that means you're going to have to multiply all these out, and then you're going to have to multiply all these out to see what you get. And if you do multiply them, you actually end up with, it's going to be x to the third plus 3x squared y plus 3xy squared plus y to the third. And if you take that one step further, make my pen a little smaller here, we're going to have x plus y, and now that whole thing that we just did. So x to the third plus 3x squared y plus 3xy squared plus x to the third. And again, you'd have to do all kinds of crazy distributing here, where you're multiplying this times everything, and then you're multiplying this times everything, and you'd end up with an even crazier polynomial here. It'll actually be x to the fourth plus 4x to the third y plus 6x squared y squared plus 4xy to the third plus y to the fourth. And for this last one, it's going to be even more ridiculous, because you're going to have x plus y times that whole thing. I'm not going to write it all out, but it will be that whole thing. And when you do all the distributing for it, you actually end up with x to the fifth plus 5x to the fourth y plus 10x to the third y squared plus 10x squared y to the third plus 5x y to the fourth plus y to the fifth. So we can make some observations from this expansion, and I'm going to actually leave this up here now so we can talk about it a little bit. I'm going to do a little bit of erasing here, though, to get rid of these yellow and red lines. So when we're looking at this, we want to make a couple observations if we can. So the number of terms in the expansion is what? I'm not going to give you the answers to these. I actually want you to think about them on your own while you're looking at this. So if you look at the number of terms in each one, how many terms are there in each one of these things? And how does that have to do with anything from our original here? So with anything from here. So the second question, if you turn the page, is the power of x starts with x to the what power, and what happens to it each time. So looking at your powers of x here, we have, this is x to the first, and then what happens here, And then what happens here, sorry, that's actually the first also, as you're going down, oops, so that's a first. So if you want to put all the ones in for all of your x's, just notice what's happening to your x exponents as you go down. So take a second to think about that. And right after that it says the power of y starts with y to the 0 and what happens to it there. So let's use purple, sounds good. So we have, this is y to the first, y to the first, and y to the second. 1, 2, 3. So you should be able to tell here what's happening to all of your y exponents. And I'm not asking for anything ridiculous, I just want you to give me some observations about what's happening as you progress through this. Next is the sum of the exponents. So what do you notice about the sum of the exponents in each term? So what are the sum of the, I'm running out of colors here. Let's use green. So the sum of the exponents. So the sum, the sum, the sum. The sum, the sum, the sum, the sum. What's happening to the sum of the exponents in each term? I'm actually going to erase all those greens because they're going to get in the way, but you get the idea of what I'm saying. So we'll go over that fourth one there also. You've already kind of answered that with question number 2. But what I will tell you is that when you're looking at this, let's use orange. So this is the first expansion, the second expansion, the third, the fourth, the fifth, and this is actually the sixth expansion. So that is one thing I want you to take a couple minutes and think about those 3 or 4 questions right there. I'm going to move on though, and we're going to talk a little bit about the coefficients. So answer these questions on your own, 1, 2, 3, and 4. And we're going to talk a little bit about the coefficients here. So I'm going to make a list of what all of our coefficients were. So we started with, our first one had a coefficient of 1. And then in the next set, we had 1 and 1 for our 2 coefficients there. Then we had 1, 2, 1. Then we had 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, and 1. 1, 6, 15, 20, 15, 6, and 1 was the bottom term there. So this diagram here is kind of interesting because if you notice, 1 plus 1 gives us 2. 1 plus 2 gives us 3. 1 plus 3 gives us 4. 1 plus 4 gives us 5. 1 plus 5 gives us 6. 2 plus 1 is 3. 3 and 1 is 4. 4 and 1 is 5. 5 and 1 is 6. And then it works in the middle too. 3 and 3 is 6. 4 and 6 is 10. 5 and 10 is 15. 6 and 4. 10 and 10. 10 and 5. It works all the way down. This is actually called, racing so much. There we go. This is actually called Pascal's triangle. I should probably write that out. Triangle. And it's made up by adding the 2 numbers above to get the one below. So, I just answered that. That was Pascal's triangle. To find the coefficients for x plus y to the n, we use the n plus 1 row of Pascal's triangle. And again, this can start to get really cumbersome if you're asked for a really far down row, like if we're asked for the 20th row or the 30th row or the 50th row. So we can also use combinations. So if we look at the 6th row, the 6th row there ended up as 1, 5, 10, 10, 5, and 1. And if we write this out using combinations, it actually is 5C0, 5C1, 5C2, 5C3, 5C4, and 5C5. So if you actually put those in your calculator, the numbers you would get would be 1, 5, 10, 10, 5, and 1. Those are the actual values. The expansion for this, therefore, once we go through all those other rules and we talk about it a little more tomorrow, the expansion for this is actually nc0 x to the n y to the 0 plus nc1 x to the n minus 1 y to the first plus nc2 x to the n minus 2 y to the second, and it keeps going on like that, where your exponent here is going up by 1 and your exponent here is going down by 1. And it keeps going on until you get to the end where you have n, the last term will be ncn, x to the 0, y to the n. So it actually reverses those exponents there. And the best part about this, the most fantastic thing that you need to know, is that this is on the reference sheet. So you don't have to memorize it. This is on the reference sheet. You don't have to memorize it. You just need to know how to use it. And it actually is a lot easier to use, which we will get in tomorrow. But for tonight, what I would like you to do is, again, think about those 4 questions for a couple seconds, and we're going to talk about the responses to that, as well as a couple examples in class tomorrow. Have a wonderful evening, and I will see you tomorrow.